slip of a belt. Sometimes the frictional grip becomes insufficient. Okay, if I have some belts, sometimes the frictional grip becomes insufficient, which means it's not enough to have it, right? So this may cause some forward motion of the driver without carrying the belt with it, right? So which means if it is driver is moving without carrying the driver with it, right? Without carrying the driver with it, which means only driver is moving, right? Driver is moving, but the follower is not following it. That's our problem. So driver is moving, follower is not following it. So here is a driver, right? This driver is moving, but the driver is not moving with this because of the slip. So which means this is slipping, right? This is moving, but this is not moving. There's some slip. This may cause some forward motion of the driver without carrying the belt with it. This may also cause some forward motion of the belt without carrying the driven pulley with it. So in other words, either the slip may occur between the driver and the pulley, or it may occur between the driven and the pulley, right? Wherever it occurs, that's a slip, right? So there is a mismatch in the relative velocity, right? This is called as a slip of the belt and is generally expressed as a percentage, right? So most of the time we express some sort of compensation for this type of mistakes, right? We won't expect 100% efficiency everywhere. So we need to give some compensation for this kind of thing. So this is kind of slip and we may express it as a percentage. So say for example, 2% of slip occurring, 3% of slip occurring, something like that we can give, right? The result of the belt slipping is to reduce the velocity ratio of the system. So if the slip occurred, what will happen? The velocity ratio will be reduced. Why? It's not working, right? It's not working. The driver is rotating, but the driver is not rotating. And not rotating in the sense it's not carrying the load with this, it's not transferring the power, right? So there is a loss of velocity ratio. As the slipping of the belt is a common phenomena, right? So this is common phenomena, right? Thus, the belt should never be used where a definite velocity ratio is of importance, right? So if you need definite velocity ratio, which means, say for example, you are expecting, you are giving some power to the driver, right? You are giving some power to the driver, and you are expecting the driven should deliver you 100 watts of power, okay? But undergoing through all this, slips, that may give you only 95 watt of power, right? So if you need 100 watts of power, you need to go for something like 105 or 107 watts. So if it is generating this much power after all kind of slip, that may bring you, or that may give you the required power. But if you set it definitely exactly for the delivered power, after the loss and all, your expectation would be down, right? That may not be able to provide what you expect. All right. So as in the example is as in the case of our minute and second arm, the watch, right? So in watch, if you know, right, if you see, these arms are there, right? They are connected with this gear type of this tooth wheel, right? So if there is any slip occurred, what will happen? There would be some delay in the motion of each arm, right? So that may lead to the change in the time, right? So say for example, for like 1 minute, if the second arm is not moving for like 2 seconds, so it's moving only for 58 seconds, which means 2 seconds is lost over there. So in each minute, 2 seconds is lost, right? So in 60 minutes, 120 seconds is lost, which means 2 minutes is lost, right? So these kind of exact motion needed areas, we can't use this belt drive, right? We can't use this belt drive. So that's what mentioned here. Thus, the belt should never be used where a definite velocity ratio is of importance, right? As in the case of our minute and second arms in a watch. So this is an example for that. Now we'll come to the equation, right? How to accommodate this slip in the equation. So V velocity I told you already, pi d1 n1 upon 60, right, if it is driver, and pi d2 n2 upon 60 if it is driven, right? If there is slip, right, if there is slip can be expressed in some percentage. Percentage, you know, if it is like 2%, if I say, that is equal to 2 upon 100, right? If it's something is expressed in percentage, that is equal to that amount upon 100. So if S is the slip, right, S percentage is the slip, S by 100 is the slip amount, right? So if S1 is the slip between the driver and the belt, right? So between the driver and the belt, the slip is S1 percentage, and slip between the belt and the follower, that is here, this is S2 percentage, right? S2 percentage. All right. Percentage means S1 by 60, right? Not 60, sorry, 100. So I will apply this one here in the velocity. So pi d1 n1 by 60 should be the normal velocity. If there is some slip, I will deduct that one by pi d1 n1 by 60 into S1 by 100, because this is the occurred slip, right? This should be the actual one. So actual one minus the slip will give you the real what happened is, right? Ideal one minus the slip will give you the actual occurrence, right? So I will deduct this pi d1 n1 by 60 into S1 by 100 from this ideal one. So if I deduct and if I solve, you can see, so I can take this pi d1 n1 outside, right? Pi d1 n1 by 60 out, okay? 1 minus, okay, I can take this 2 out, 1 minus S1 by 100, right? So velocity now is pi d1 n1 by 60 into 1 minus S1 by 100. So this is to the slip occurred in the driver. Why? S1 is a slip in the driver, right? Similar way, this can be applied in the driven also, right? So driven also I'm going to apply the same. So what will happen? Pi d2 n2 by 60. So that will be turned as pi d2 n2 by 60 minus pi d2 n2 by 60 into S2 by 100, right? So that is pi d2 n2 by 100, sorry, n2 by 60 into 1 minus S2 by 100, right? So this is for driver, this is for follower, right? So now there is two slips occurring. So
Yes,
now
sir.
what I will do is I will multiply these two, right? So that will give you n2 by n1. So this is our usual equation, right? N2 by n2 is the usual equation. That's the ideal equation, is equal to d1 by d2, right? d1 by d2. This is the actual equation. From this, I need to solve this one, right? I need to reduce this lost part, right? So that is, from here you see, pi d2 n2 by 60 is equal to pi d1 n by 60 into 1 minus S1 by 100, okay? 1 minus S1 by 100 into here 1 minus S2 by 100, right? 1 minus S2 by 100, right? So when I solve it, n2 by n1, right? n2 by n1, this pi and 60 would be cancelled out, equal to d1 by d2, okay? n2 by n1 is equal to d1 by d2, okay? d1 by d2 into 1 minus S1 by 100 minus S2 by 100. And here we are neglecting one term, okay? So if you just multiply this one, you know, 1 into 1, 1, okay, it's there. 1 into S2 by 100, that is there, right? 1 into S2 by 100. S1 by 100 into 1, that is minus S1 by 100. S1 by 100 into S2 by 100, that is S1, S2 by 10,000, right? S1, S2 by 10,000. We are neglecting that particular term because this is too small. Why? If it is 2%, if I just replace it with 2, S1 and S2, so 2 into 2, that is 4. 100 into 100, 10,000. So 4 by 10,000, that will be like something 0.00004, right? So due to the smallness or of that particular value, we are neglecting this term. You see here, S1, S2 upon 100 by 100. This term we are neglecting. Even if you put it, it won't make any big difference, right? But if you see here, this is 2 by 100 and this is 2 by 100, right? I'm just saying for an example, if 2% is the slip, this is 2 by 100 and this is 2 by 100, right? So 1 minus 2 by 100 minus 2 by 100. So 100 by 100, that would be 96 by 100, right? So 96 by 100 and 95.9996 by 100 is not big difference, right? So that's for the easiness, we are neglecting that term, which is very small, all right? So which will be giving you d2 by d1 by d2 is equal to 1 minus s1 plus s2 by 100, right? 1 minus, I am taking this minus in common, s1 plus s2 by 100, right? Which will be equal to d1 plus d2, d1 by d2 into 1 minus this s1 plus s2. I am commonly naming it as s, right? Combinedly, I am naming it as s. So 1 minus s by 100, where s is equal to s1 plus s2. So if the driver's slip is 2% and driven slip is 3%, we can add them to here and put them as 5%, right? So that is why this is s1 plus s2 is the combination of both the slip edges, and I can put it commonly as s, right? So d1 by d2 into 1 minus s by 100. So your final equation would be d1 by d2, right, into 1 minus s2 by s by 100, right? n2 by n1 is equal to d1 by d2 into 1 minus s by 100, right? That would be the final equation, right? If you consider the thickness also, right? If you consider the thickness also, then as previously done, the thickness would be added with the diameters, right? So that is going to be n2 by n1 is equal to d1 plus t upon d2 plus t into 1 minus s by 100. So this is going to be a final equation if the thickness is considered, and this is going to be a final equation if the thickness is not considered or thickness can be neglected, right? So this is the equation to find the slip of the belt. An engine running at 150 rpm, okay? So now the rpm of the driver is given. Drives a line shaft by means of a belt, okay? Means of a belt. This is a compound belt. Above from the diagram, you might have understand. The engine pulley is 750 millimeter diameter, right? Engine pulley is 750 millimeter diameter, and the pulley on the line shaft being 450 millimeter, right? Pulley on the line shaft is 450 millimeter. A 900 millimeter diameter pulley on the line shaft, right? So here is the line shaft, which means this is going to be the line shaft. So again, the sentence 900 millimeter diameter pulley on the line shaft. So that pulley is also going to be on the line shaft. Drives a 150 millimeter pulley keyed to a dynamo shaft, right? 150 millimeter pulley, which is keyed to a dynamo shaft. Okay. Find the speed of the dynamo shaft, right? We need to find the speed of the dynamo shaft when there is no slip, right? So we don't have to consider the slip. And if there's a slip of 2% at each drive, 2% at each drive, you need to consider 2% at each drive, which means driver also there is 2%, driven also there is 2% slip, right? Now we'll see how are we going to solve this numerical. So the data given, n1 150 rpm, right? n1 150 rpm, that is last driven. d1 750 millimeter, right? d1 750 millimeter. d2 which is given 450 millimeter. d3 900 millimeter. d4 150 millimeter, right? Arrangement of the belt drives is shown, okay, in the diagram. Set n4 speed of dynamo shaft. Okay, now we will apply it in the equation. So we have all 4 diameters, and also we have the rpm of the engine, right? rpm of the engine shaft. So that is n1 is also given, right? So according to our equation, we will have, since this is compound drive, right? This is compound drive. What we are going to do? We have to apply the compound drive equation. So according to compound drive equation, we know n4, that is last driven, that's over here, upon first driver, right? First driver equal to d1 by d2 into d3 by d4, right? This is the equation we know. Now we will substitute those values, right? N4, that is last driver, that is what asked to be found, we don't know, over N1, right? That is first driven we know, that is 150, it is given, equal to d1 by d2 into d3 by d4. So d1, d2, d3, d4 are given. d1 is 750, d2 is 450, d3 is 900, and d4 is 150, right? So when you solve it, you will have 750 into 900 by 450 into 150. So this 150 and this 150 will be cancelled out. We will have 10 as the velocity ratio, right? So now what you have found is the velocity ratio. You are asked to find the velocity of the dynamo shaft. So with the velocity ratio, you need to multiply the first one, right? So 150 into 10 will give you N4 is equal to 1500 RPM, right? 1500 RPM. This condition is for when there is no slip, right? When there is no slip. Now, if there is slip, right? So if there is some slip, then we know the equation is going to be turned like this. So N4 by N1, that will remain same, right? Last driver upon first driven, last driven upon first driver equal to d1 by d3 by d2 by d4, right? d1 into d3 by d2 by d4, that will apply as it is. Now we are going to accommodate the slip, right? That is 1 minus s1 by 100 into 1 minus s2 by 100. So this is the slip on the driver and this is the slip on the driven, right? Or else we can simply put 1 minus s1 plus s2 by 100 also, right? Both will give you same answer. So now we have found all these things. N4 is the question. N1 given in the question 150 RPM. D1, D3, D2, D4, D all are given here. D1 750, D2 450, D3 900, and D4 is 150, right? Into 1 minus slip was given 2%, right? 2% slip means 2% slip at each pulley, right? Each. So where we are going to put 1 minus 2 into 100, right? If it is percentage, then divided by 100, 2 into 100, 2 by 100 into 1 minus 2 by 100. So this is for driver and this is for driven, right? So when you solve it, you will have 1 minus 2 plus 2, 4. That will be 9.6, right? So the velocity ratio is reduced from 10 to 9.6 due to the slip edge, right? So your final velocity of the dynamo shaft would be velocity ratio into the first driver, right? So 9.6 into 150, right? 9.6 into 150. That is equal to 1440 RPM, right? 1440 RPM. So without slip, it was running at 1500 RPM, but with slip, 60 RPM reduction is there, right? So you see, just 2% is the slip, right? Just 2% is the slip. But for that 2%, the loss occurred is 60 RPM, right? So this is how we solve this numerical. Okay. So this is without slip and this is with the slip.